Good afternoon. I hope you're doing well and you're safe. I think we can start, and the other students they can join us during my lecture. Let me first share my file. Okay, we continue with the power. Okay, so the last concept in this section is the power. And if we have a system which is subjected to the external force F and the couple M, which is acting on this system or the rigid body, we can obtain the total instantaneous power for this system, which is equal to F dot V and plus M times by omega. Here we call it instantaneous power because in this equation, this V is the instantaneous velocity and omega is the instantaneous angular velocity. So this power is just for a specific moment, and by changing the velocity and angular velocity, or maybe the changing the force and couple, this power will be changed. So we have the power which it can be positive or negative, and if the sense of the moment this couple or force and omega or velocity was the same, we can say that the power is positive. And when the power is positive, it means that the energy will be supplied to the rigid body and the level of the energy will be increased. Okay, so this is the total concept that we just want to mention in this section. And in fact, this is the last concept. Now we can solve some examples. It was remained from the yesterday, and now we can continue with some examples. Any question from the theoretical formulation for this section? If you have any question, please ask. Otherwise, we can continue with the examples. Okay. Okay. We start with one example. Here we have a wheel which is rolls up the incline on its hubs without slipping and is pulled by the 100 Newton force applied to the cord wrapped around its outer rim. At this point here, you can see if the wheel starts from rest, compute its angular velocity omega after its center has moved a distance of 3 meters up the incline. So the displacement of this point, the center of this wheel, will move 3 meters in this direction, up in upward direction on the incline. The wheel has a mass of 40 kilogram with center of mass at O and has a centroidal radius of gyration of 150 millimeter. So this wheel is rotating without slipping according to problem description here, without slipping. So the first point that we can conclude from this point is that the acceleration of the mass center of the wheel is equal to r times by alpha, which alpha is the angular acceleration of the wheel and r is the position of position vector of the mass center with respect to the contact point, which is here. Now we can write and solve this problem. Here we can use two different methods. One is the Newton's second law, and the second one we will use the work and energy equations. But first, I have a question. If you want to solve this problem according to this point, which the motion is without sleeping, we can assume the motion as a pure rotational motion. About which point, can you tell me? No. Yesterday I mentioned when we have rotation without sleeping. In this case, for example, we have rotation without sleeping. Exactly, thank you. Yes, we can assume that this wheel is rotating about this point, if we call it, for example, C, the contact point. And we can assume that this wheel has a pure rotation about this point C, and we can assume that this is a pin connection, and this wheel is rotating about this pin C. So let's start to solve this problem first using the Newton's second law. Okay, this is the free body diagram for this wheel. When you want to use the Newton's second law, the first step is to obtain the free body diagram of the system or the body. Here we have a wheel. It's subjected to a 100 Newton force, this external force. It has a weight which is subjected exactly on the mass center, which is point O, according to the problem description. We have one friction force F here and one normal reaction force N, which is located exactly at this contact point, which we call this point C. We assume this coordinate system X, which is parallel to the incline, and the positive direction of x-axis is in upward direction. So now we can write the force equation in x direction, the moment equation, and obtain the acceleration. Because this is a without a slipping motion, so we can assume that the acceleration ax is equal to the radius times by alpha, which alpha is the angular acceleration of the wheel. So this is the point, and we can use this point to decrease the number of the unknowns and solve this equation for acceleration. So if you write the force equation, the first one, in x direction, we will have this 100 Newton force. We have the 100 Newton force. Also, we have the force F, this one, and the x component of the weight. So we will have 100 plus F, both of them are in upward direction or in the positive direction of x-axis. And the x component of the weight, which is W times by sine 15. So this, sorry, can you hear me now? Because my connection has had some problem and it was disconnected again. Can you hear me now? Okay. Okay, let's continue. So we can write the force equation in x direction. As you can see, 100 plus F minus W sine 15. This is the summation of the force in x direction. It must be equal to the mass times by the acceleration in x direction. And the second equation is the moment equation about this point O. Okay, and this point is the mass center. If you write a moment equation about this point O, we will have one moment due to this 100 force, this force. We have the, do you have my voice now? Can you hear me? Can you hear my audio now? Is it clear, my audio? Okay, is my audio clear now? Okay, okay, so we write the moment equation. I don't know what is the problem because my connection is good, but I don't know why it disconnecting. Is my voice clear now? Okay, so we continue. So we have the moment equation about point O. If we write the moment equation, we will have the moment due to this force 100 Newton and the moment due to the friction force. So the arm for the 100 Newton force each is 0.2, and the arm for this force F, the friction force, is 0.1. And if you write this equation, we need the mass moment of inertia about the mass center, which IO, and you can easily, using the radius of gyration, you can calculate the mass moment of inertia. Now you can solve these two equations and obtain the angular acceleration and the friction force F for this problem. So we can substitute here in the first equation. Instead of ax, we have 0.1 times by alpha. And if you solve these two equations, you can easily obtain that alpha is equal to 1.52, which is the linear acceleration of the mass center. Now, when you calculate the acceleration in this motion, you need to obtain the velocity after 3 meters going upward in upward direction. So we have the equation, the independence of time equation. This is the independent of time equation because the acceleration is constant. As you can see, the acceleration is a constant value. So you can use this equation, v squared minus v naught squared, it's equal to 2 times by as, because this will start at rest. Initially it was at rest, so the initial velocity v naught this term is equal to 0, and v squared is equal to 2as, and we know that s is 3 meters in upward direction. So easily you can solve this equation and obtain that v, the velocity after 3 meters going upward, is 3.02 meter per second. Now to obtain the angular velocity, we know that omega is equal to v divided by r from here, and r is this distance. As I told you, we can assume that this wheel has a pure rotational motion about point C, or the contact point. So when it has a pure rotational motion, and we know that the velocity of this mass center V is equal to 3 meter per second. So the angular velocity is equal to this V divided by this radius, which is 0.1. So this is the angular velocity, 30 radian per second. And the next slide, we will solve this problem using the work and energy equation. Okay. Any questions so far? Is it clear? Is everything clear? Sorry, again, my connection was some problems. Can you hear me now? Okay. So we solve this example using the Newton's second law. And do you have any question from this example? Is it clear now? Is everything clear? Okay, so now we can solve this problem using the work and energy. To find the response, again, we have the same free body diagram as you can see. Now we want to use the work and energy equation. Here in this system, we know that the work done by the W1 to 2 is the work done by the external forces other than the weight or a spring force. Here, so we should neglect this, the W, the weight of the wheel, and we will have three external force, which is 100 Newton, the other one is N, and the other one is F. So in this case, if you write W1 to 2, we will have 100 times by dA, which dA is the displacement of point A. This is the point A. And here you can see we neglect the work done by F and N. Can you tell me why we neglect the work done by these two forces? Any suggestion? No, we have friction here according to the problem description, because the rotation is without a slipping. So definitely we have the friction, and this is the friction force F. We call it friction force, that we call it F. In previous method, in the first method that in previous slide we solved this example, we even obtained the friction force. Here we have the friction and we have the normal force N. In fact, this wheel is subjected to three external force, which is the 100 Newton, with the other one is the friction force, and the last one, which is this N, the normal reaction. But in the work done by the external force, we only consider the work done by this 100 Newton force, and we neglect the work done by F and N. Can you tell me why? Any other suggestion or idea? No idea? Here, I told you when we have the rotation without a slipping, it means that this point C, the connection point, if you call it point C, this point is like a fixed point that the wheel is rotating about this fixed point. We can assume that this point is a pin connection. So when we have a pin connection at this moment, assume that at this moment here we have a pin. So this wheel is rotating about this pin at this moment. So what does it mean? It means that the displacement of this point is 0. Okay, so it means this point C will be a constant and a stationary point, and it means that this point will not move. So when the displacement of this point is 0, it means that the displacement of force F and N for both of them is 0. So the work done by these two forces are 0. So only we will have this 100 Newton force, this term, multiplied by dA, which dA is the displacement of point A. And to obtain the dA, we can use the geometry of this problem. Here, assume that we have a triangle. This edge is dA. This point is the displacement of yes, if we had a slipping here, force, the friction force will do some work, but again N will not do any work because N is perpendicular to the direction of the motion. Here in, let me show you in the first slide. Here you can see this is the work done by the force. It's equal to F dot V. Yeah, sorry, this is power. Let me go back another slide. Here Here you can see this is the work done by the external forces. It's equal to F dot dr, and it's equal to F cosine alpha ds. So anytime when this alpha is equal to pi divided by 2, this work will be equal to 0. For the friction force, when we have the normal reactions, the normal reaction is perpendicular to the direction of the motion, as you can see here. When this wheel is rotating with slipping, this point C will move in this direction, and the normal force N is perpendicular to the direction of the motion. So again, the work done by force N is 0, but the work done by this force F is not 0. Okay, clear? Okay, so now we can, as I told you, to obtain the dA, or this displacement of point A, we can use this triangle. This is the triangle, as I told you. Here, this vector, this is dA, okay? And this length is DO. If you write in this triangle, according to the geometry, you can write that the ratio of dA to DO, or dA divided by DO, is equal to this length, which is 200 plus 100, divided by this small length, which is 100. Or from the geometry, you can find the relation between the displacement of the mass center point O and the displacement of point A. And you can conclude that the displacement of point A is 3 times by the displacement of point O. The point O, which is the mass center, will move 3 meters. So the displacement of point A is 9 meter. Okay, so we can substitute, and finally you can find that W, or the work done by this 100 Newton force, is equal to 900. Okay, and the second step, we need to obtain the kinetic and potential energy. The kinetic energy, the initial term of the kinetic energy is 0 because it starts from rest. The final kinetic energy in the second position is half times by mv squared, which v is the velocity of the mass center, plus half times by I o omega squared, and IO is again the mass moment of inertia about the mass center. And we know that VO, or the velocity of the mass center, is equal to the radius times by omega. Similar to the previous method, we know that this is a motion without a slipping. So when we don't have a slipping, the velocity of the mass center is equal to the radius times by the angular velocity. So this is a T sub 2, or the final kinetic energy. You can substitute and simplify this and obtain in terms of omega. The second method that you can obtain the the kinetic energy, in this case in the final position, we can use the equation of the uh, by considering the instantaneous center of zero velocity. Okay, so in this case, if you want to obtain the kinetic energy in the second position, or in the final position, you can write half times by I c times by omega squared, which I c is the mass moment of inertia about this connection point. This is point C. If you write the mass moment of inertia about this point, the kinetic energy is equal to half times by IC times by omega squared. So this is up to you. You can use that form. And now we need to obtain the potential energy. The initial potential energy, we assumed, is equal to 0 because we consider the initial position is the datum level. The final potential energy is equal to mgh, and h is the vertical difference from the initial position. If we assume that the initial position is 0, here we have one incline. This is the initial position for the wheel. This is moving 3 meters in the parallel direction of incline. Okay, so this red line is 3 meters, but the change in the vertical position of this center is equal to this length. Let me show you. Where is my mouse? Here. So if we want to find h, this is the h, and this h is equal to 3 times by sine 15. This angle is 15 degree. So if we call it h, this h is equal to 3 times by sine 15. Okay, so this is the h in the potential, gravity potential energy. Now we can substitute, and v sub 2, which is mgh, and it will be 304.37. Now we can substitute w, t, and v in the energy and work and energy equation, and we can easily obtain that omega, the angular velocity, is equal to 30.2 radian per second. Okay, any question? Is everything clear? Okay. Okay, the next example, we have a slender rod of mass m and length L, has a particle with negligible radius and mass 2m. So the mass of this particle This one is 2m attached to its end. If the body is released from rest when in the position shown, determine its angular velocity as it passes the vertical position. So we release this system from rest and we want to obtain the velocity as it passes the vertical position. So when this mass 2m is located exactly under point O. This problem is clearly we can use a work and energy method in this type of problems when we have a change in the level of the gravity potential energy. So easily you can use the work and energy equation. But you also can use the Newton's second law. I mean, if you want to use the Newton's second law, you can plot the free body diagram for this system. Here you can see we will have two reaction force at point O. We can call them OX and OY. We will have the weight for the slender rod and the weight for this particle, which is 2 mg. Here we have mg, we have 2 mg. And if you write the force equation, the moment equation about this point O, you can see by rotating this rod about point O, the direction of mg will be changed. So it will be a function of theta. For example, if we assume that this angle is theta, you can write the force equation about this point, point O using this theta, and it will be to somehow a complicated procedure. You should obtain the angular acceleration and also you should obtain the angular velocity, and then you can find the final velocity. But the best option for this type of problems is using the work and energy methods, because you don't need to obtain the acceleration and you can directly find the velocity, final velocity using the initial velocity. Here the initial velocity is 0, so T1 or the kinetic energy at initial position is 0. We can assume that the datum level is this level, the initial level. So this is the datum level. At this level, the potential energy, the gravity potential energy is 0 and there is no spring. So V is equal to 0. The work done by the external forces is again 0 because there is no external force here. We only have the weight and this reaction at point O, which they are the internal reactions. So T1, V1, and W sub 1 to 2 is equal to 0. So these terms are 0, and we only have the kinetic energy in the final position and also the potential energy in the final position. So T sub 2, which is the kinetic energy in final position, is equal to the kinetic energy due to the slender rod, this term, and the kinetic energy due to the particle 2m. So we will have for the particle, it's clear because this is a particle, its kinetic energy is equal to the half times by m times by the velocity squared. M for this particle is 2m, the mass is equal to 2m, so we will have half times by 2m times by Vp, which Vp is the velocity of this particle squared, and plus now we can write the kinetic energy for the slender rod. The kinetic energy for this rod is equal to half times by the mass times by the velocity of the center, because here we have rotation. When we have rotation, we will have the kinetic energy due to the translational motion. Here the translational motion, here we have Vg, and also the kinetic energy due to the rotation, which is half times by Ig omega squared. Or instead of this mvg squared plus Ig omega squared, we can substitute instead of this term you can write the kinetic energy about point O again, because here we have a pure rotational motion about point O. So if you write the kinetic energy about point O, we will have half times by I-O omega I squared. So instead of these two terms, you can substitute I-O omega I squared, of course, times by half. Here we have half times by I-O omega squared. So this is the kinetic energy in the final position, and this is I. And we need the potential energy in the final position when this mass 2m is located under the point O, or the cylinder is in vertical position. The mass of the particle, which is 2m, located 3 times by L divided by 4 under the datum level. So we will have minus 2m times by g, and h is 3l divided by 4. And again, the mass center of the cylinder rod is again under the datum by L divided by 4. So the gravity potential energy for this cylinder rod is again minus, because it's under the datum level, times by m times by g times by L divided by 4. So now we can substitute T sub 2 and V sub 2 and simplify and obtain the velocity of the cylinder rod. Yeah, as I told you, the kinetic energy, you can write the kinetic energy instead of this mvg squared plus half ig omega squared. You can substitute I o omega squared. Okay, so it's up to you, and you can use this. And Vp and Vg, which are the velocity of the particle and the velocity of the mass center respectively, are equal to their lengths times by their omega. Their length is the distance between the point and point O. For the particle, this length is 3L divided by 4. And for the mass center is L divided by 4. As you can see, this is L divided by 4 omega, 3L divided by 4 omega. And Ig for the cylinder, which is the mass moment of inertia above the mass center, and it's equal to 1 divided by 12 ml squared. So you can substitute and simplify, and finally you can obtain the angular velocity. So if you substitute and simplify, we will have ml squared in all of the terms. You can cancel out with mgl in the right hand side, and you will have omega squared is equal to this term, or omega, which is related to the length of the cylinder. Okay, so only the parameter L, or the length of this cylinder rod, will affect on the angular velocity omega. Okay, any question? Clear? Okay, because my time is almost finished, we can have a 10 minutes break. Now it's about 15 minutes to 5. We can start 5 minutes to 5. We can start the second session. Okay, so we can have about 10 minutes break, and then we can continue the lectures. Okay, so have a short break, and I will see you again. Thank you.